Okay. So the plan today is to test our installation. Last time we discussed what should we install, and this time we want to go through Mandelbrot Set, how to plot it with all these codes that the compilers that we want to have, and I'm going to comment on the implementation in Fortran, in C, and Python. But before we go that, I want to show this popularity of different programming languages. So here I have a plot from I think was 2021, where I was trying to argue that Python is very useful because well, clearly the popularity is increasing pretty steeply. I started to teach in Python back in 2016, where it was very hard to make the case that Python is really something that is important and useful, let's say beyond small groups in condensed matter. But today, this is kind of obvious. If you go to the latest, this programming community index, and you check Python, you see that it's currently the first, is the top. So clearly it's winning against all other languages, including C, Java, C++, and so on. And probably the reason for this has to do with data science. So from 2018 up, it's very clear how steep the rise was. And this is when Google produced their machine learning capabilities in Python. And from then on, it seems that Python is seeing a huge boost. And also, I could say that the scientific community, by and large, is adopting Python. Of course, scientific community is usually a little bit behind because there's a lot of legacy code. But the nice thing about Python is that we will show how to integrate legacy code using Python. And of course, that then somehow we have no real excuse why not to adopt that. Now, of course, C was historically always important and still is important here because it's a basic language in which all the operating systems are written, including Windows and Unix and Mac OS. But of course, the C is kind of language that it's not most appropriate for scientific work because it's hard to manipulate high-dimensional arrays. It doesn't have anything, any containers for high-dimensional arrays, for example. And even complex numbers were added relatively recently as a C standard. Now they exist, but they didn't exist for a long time. So Java used to be very popular back in the day, but as you can see, Java is kind of dropping with time. My understanding is that this has to do with web programming. Java was very popular when web programming was important, but as far as I know, most of the web development now is done with very specific tools, and we don't need so much anymore low-level Java programming. C++ was always there, never overwhelmingly important, but still, at least in scientific community, it's still something that we need to be aware of. And of course, Fortran doesn't make the cut. I mean, it's somewhere in the noise. Nevertheless, in science, we do have lots of Fortran codes, and so in some sense, we need to be aware of them. But nevertheless, the message here is that Python is up and coming, and even if you stay in physics, you're going to need it. If you go into some other job, you will probably use Python as well. So that's good to know. Okay, so the testing today is going to be done on Mandelbrot Set. So we're going to plot Mandelbrot Set with different programming languages, and we're going to check how to use this parallelization in Fortran and in C. And we're going to see how much difference in terms of time does it make to write things in a low-level language, such as C. Okay, so what is Mandeville set? I guess you're probably familiar with that, but let me repeat. You see my screen, isn't it? You see the screen here. You do, huh? Okay, so Mandelbrot set is this nice plot of the points which are part of the Mandelbrot set. It appears black here, and it's obtained by plotting a very simple sequence, basically quadratic or quadratic polynomial in complex plane. So x-axis here is corresponds to the real part of a complex number z0, and y-axis corresponds to imaginary part of the complex variable z0. And we define a function f of z, which is written here, z squared plus z0. So the z0 here is the one that's being plotted. And so what we do is we repeat this f many, many times. So the idea is we start with 0, and then we calculate f of 0. Then in next iteration, we calculate f of 0, and then f of 0, and so on. And we repeat this infinite number of times, let's say. And the question is whether this sequence is bounded, is less than infinite. In other words, it doesn't go to infinity, or it tends to infinity when n goes to infinity. So that's the question. And of course, this nice chaotic plot, self-similar plot actually, is obtained when we define the points which remain bounded when we repeat this function many, many times. So what we need to do is specified here precisely. So we start with calculating f of 0, which is just z0, because that's the definition of f. Then when we apply f of 0, which is of course f of z0, which is z0 squared plus z0. Then f of 0, which of course is f of this previous value and becomes z0 squared plus z0, and so on. And so clearly, if z0 is 0, then all these numbers are 0, and the number here in the center is bounded, is part of the Mandelbrot set. But if z0 is 1, for example, which is here, 1, 0, isn't it? So if z0 is 1, then you see there is 1, then it's 2, and here would be what is 2 squared of 4, 5, and so clearly it tends to infinity when n goes to infinity. While minus 1, for example, minus 1, 0, this point here, it's bounded because z0 is 1, but z0 squared plus z0 is actually 0. And then here it's 1, and so on. So it iterates between 0, 1, 0, 1, 0, 1. So it's still part of Mandelbrot set because it's finite. So how do we check if something is part of Mandelbrot set or not? Standard algorithm is that we repeat this large number of steps, and then we check if the value after many steps is either less than 2 or bigger than 2. So as we see, 1 is okay because if the value is 1, it might alternate. But once it becomes bigger than 2, we are absolutely certain that we can jump out of the loop and we can declare that this sequence will diverge. Okay. Of course, to determine very, very precisely whether something is part of Mandelbrot set or not, we would need to iterate this infinite number of times. But of course, nothing is infinite in computer. So typically what we're going to do is we're going to use something like 1,000 iterations. Now, to demonstrate how this looks like, I'm going to use the dynamic Mandelbrot set. Let me see, ManP dynamic. So this is the Mandelbrot set that we're going to eventually develop. And this one shows you, basically updates the Mandelbrot set when you select certain region. So we start with plotting from -2 to 1 in X direction, and from -1 to 1 in Y direction. And then we can select certain region here, for example, like this, and replot. And when we replot, you see that the Mandelbrot set looks just like the previous one, doesn't it? So this is called self-similarity. So Mandelbrot has this nice feature that things are self-similar. So we zoom in and we see almost the same Mandelbrot set, doesn't it? And we can do this several times. So we can select now this little dot here, and you know, see, look at it. It's again the same Mandelbrot set. Okay. And we can probably do one more time, and then it starts looking kind of scrambled. So this one, 10 to the -5 right now. You can still clearly see that's what the Mandelbrot set is, isn't it? And then eventually, I think, after many iterations, we are not gonna, yeah, this one, this shape is not anymore the same. So kind of.
Professor, I have a question.
Yes.
Does it change shape because like there's round off error, or is that like actually like how it happens naturally?
Yeah, so I mean, in exact theory, we know that it should remain self-similar forever. So this is clearly some error. Now, what is the biggest issue here? Well, there are several, but I think the biggest issue right now in this plot that I've created just right now is the number of iterations. So I have 1,000 iterations. If I had 10,000, I would probably be able to do one more iteration. But it turns out that eventually I'm going to be stuck with round of error, as you said. I mean, double precision will also kill me, probably 10 to the -14 for sure, but even sooner probably. So yeah, there are several issues. Round of error is one, but I don't think that the round of error is right now yet playing the role. I think that this time we could actually experiment. This is something you can do at home. You could increase number of steps, and you will probably be able to do one more step. Okay, but yeah, sooner or later, round of error should be overwhelming problem. Yeah, so of course this playing with this Mandelbrot set is very nice. So in Python, that's easy to do, and we're going to implement this dynamic adjusting of the Mandelbrot set. Now, of course, in other languages, we are going to just select a fixed region to plot, and then we're going to print result into the standard output, into the file actually, and then use GNU plot to display, because Fortran and C don't have a standard way of plotting, doesn't it? So we're going to use GNU plot with Fortran and C. Now, eventually we will use Python for plotting, because Python can be, of course, merged together with C to speed it up. And that's probably let's say, the best of both worlds. So we have speed of C and plotting of Python. Okay, but let's start slowly. So first language is going to be Fortran. You might ask why Fortran? It's a really old-fashioned language. Well, lots of legacy code is still there, and when we combine it with Python, is actually not a bad way of speeding up Python code. Okay, so what's required for Fortran? So here is the main part of the program. Fortran can have either function or subroutine. So subroutine means it doesn't return anything. Function means it returns a type. So in this case, we are returning integer. And in particular, we're going to return how many steps did we need before. So here we return how many steps did we need before we realized that something is not part of the Mandelbrot set. Okay, so how many steps do we need before we realize that Z is bigger than 2? which means that it's not part of Mandelbrot set, and we return, doesn't it? So that's going to be returned. We are going to return in all cases number of iterations that we need before we understand, before the number escaped from the Mandelbrot set, let's say. Okay. So this statement here, implicit none, in all codes which I write, I always put implicit none here. Of course, in some scientific codes that you're going to see, this statement might be absent. And it's a very good idea to always write this implicit none, but this statement comes from historic reasons. Back in the day when the codes were very short, people assumed that certain variables that start with I, J, K, L are always going to be integers. Those that start with A, B, C are going to be always real numbers. And those that start with W and Z are going to be complex numbers. So there was some typical assumption of what the name of the variables is. Of course, in modern coding, this basically doesn't have any room, because there's just too many possibilities for making an error. So why is this so problematic? Because typically when you write a long code, it's so easy to misspell a variable. And when you misspell a variable, this compiler will not issue an error or warning that there is a new variable appearing. It will just work, but it will produce nonsense. So therefore, it's a good idea to always use implicit none and force Fortran to ask you to define each variable. So this basically forces you to define each variable, to write what the variable type is. Now, this, of course, is default behavior in C or in C++. You cannot have a variable without defining it. Of course, in Python, you could say that we never define any variable, but the difference is that in Python, there is so-called dynamic typecasting. So in some sense, of course, we don't define the variables, but we still get an error if you start using a new variable somewhere in the middle of the code without first initializing it. So Python does check whether the code makes sense or no, but in Fortran doesn't if you don't have implicit none. So this is a statement that is kind of historic, but it's important to use it if you want to have code that is kind of not so error prone. Okay, so then here we define variables. So Fortran always requires one to define variables, all the variables at the beginning of the subroutine or function. In this case, we need complex variables Z0 and integer variable how many steps we have. So these two variables are, of course, the input variables, Z0 and max steps. And this intent in defines that the variable is an input variable. So this intent in is actually not essential. It's useful to write it because you kind of explain to the compiler that this is an input variable and it shouldn't be changed. So in some sense, this is equivalent to saying in C that this is constant for this subroutine. So it's not going to be changed because it's intent in. You can have variable which is intent out, which means it's an output variable. It could also be in out, which means that it's input variable, but it's allowed to be changed. It can be returned. So, but these ones are just input in, which means that there are only input variables, cannot be changed inside the function. Clearly, this complex 16 means that this complex number Z0 has 16 bytes. Now, as you probably know, a typical double precision number, which is called a real 8 in Fortran, has 8 bytes. And this is a standard floating point number, double precision floating point number, which is available, of course, in Python, or standard floating point number in Python. It's called double in C, and it's called real 8 in Fortran. Now, if you have two double numbers, then, of course, this corresponds to complex, and therefore complex has 16 bytes because it's two 8-byte numbers. So we want to have this double precision. Of course, alternative is single precision, which is called complex 8, or in floating point, it's going to be real 4. but this has very low precision, so we will have problems even zooming in probably twice, and we're already going to see error. Okay, so we have the complex number, and then we have the integer max steps, how many steps maximum we are going to try. And then after that, we need to define local variables. So again, Fortran requires all variables to be defined at the beginning of the code. Now, this mark here, what is it called? This designates that we have a comment. Locals, for example, here it's a comment. And then this part here is actually the algorithm for the Mandelbrot set. We define complex number z, and we define integer counter. So this I here is going to be a counter that counts how many steps we've done up to now. And then we start, of course, with z setting to 0 as required by the algorithm. And then we do we try to do as many steps as maximum number of steps. That is an input variable. So this is a typical statement to repeat. So this do statement is the most common statement in Fortran. It's equivalent to for loop in C++ or Python. So both Python and C++ use for loop. So for I in range, for example. We're going to use this many times in Python. For the equivalent statement in Fortran is do I is 1 to max steps. Now, if you want to keep Fortran almost the same as, well, as similar as possible to Python, we would use do I is 0, I is max steps minus 1. Why is that? Because in Fortran, in Python, we always start iterating from 0 and then to the variable which is less than the upper bound. Okay, so for loop in Fortran or in for loop in Python always means start with 0 and less than the max steps, let's say. But in Fortran, it's very different. So we almost always start with 1, and then we iterate up to max steps, including max steps. So the big difference is that this last number here, it's going to appear in the loop, max steps. Okay, that's different than in C and in Python. Now, why the do loop typically looks like that? It has to do with array variables. So in Python and in C++ or C, the arrays are counted from 0. So A of either 0 or A of 0 is the first variable available in an array. But in Fortran, we always start with 1. A of 1 is the first variable available. So A of 0 will always result in an error. So, and that's the reason why we always start loops from 1 to including the last number in the do loop. Okay, so we go from 1 to the last number in the do loop. And so what do? Well, we set new z becomes z squared plus z naught, isn't it? So that's what Mandelbrot set requires to evaluate this function, and then assign the result to z, and then we iterate this many times. And then before we start the new iteration, we check if the z is still part of the Mandelbrot set. If we still believe that this z is less than 2. And so the way to do it is we check if absolute value of z is bigger than 2. Then we know that this thing is not part of the Mandelbrot set, and we return a number of iterations that was required, and then we jump out. So this return means we jump out. So this is different than in Python and in C. Again, in Python or C or C++, we will always say return, and then we're going to give here a variable that we want to return. But in Fortran, the syntax is different. We have an empty return statement that doesn't do anything, but we have to assign return is empty, so there's nothing. But we need to assign to the function name. So the name of the function is Mandelbrot. We need to assign the variable to the function name. Kind of unusual, isn't it? So function name is Mandelbrot, and we need to assign the return variable to the function name, and then return has nothing. Okay. Anyway, that's the syntax. So this is the main do loop that we need, and then if we survive all the way up to here, then we know that this variable, this number z0, is part of the Mandelbrot set, and if that's the case, we're going to assign Mandelbrot to be max steps, which is in this case 1000, and yeah, so we're going to know that if the return value is very large number, then this is part of the Mandelbrot set. Okay, so this is the part of the code, part of the main routine, but we also need to have a program which calls the function that we just defined. And of course, this program itself needs quite a lot of code as well. So let me go through this program and explain roughly what it does. So every program in Fortran needs to start with program, name of the program, and has to end with end program, name of the program. So this particular code is written in so-called Fortran 90, which is a little bit more structured. Fortran 77 is very hard to read because it's not even justified. Now, Fortran 90 is, of course, much more readable and kind of similar, more similar to more modern language. So therefore, that's usually the thing that I use or that I show. But Fortran is always back compatible. So in other words, if you have a very old code, Fortran 77, and you use the same compiler will actually be compatible, will compile the code. Okay, so the first line or the first few lines here after the program call possible modules. So Fortran 90 allows modules, and I'm going to use here the module for OpenMP. So this is OpenMP module. Why? Well, because we're going to make this code OpenMP parallel. As I said before, Fortran and C++ are kind of straightforward to make OpenMP parallel. So therefore, we're going to do that. And more importantly, this library contains this routine to get wall time. Okay, wall time.
Professor, I have another question.
Yes.
What's like the difference between like using OpenMP versus like using threads, like using like concurrent threads?
That's the same thing.
Oh, it is?
Yes.
Oh, okay.
Yeah, that's the same thing. So, I mean, it's awkward to code itself how to use threads. I mean, OpenMP is a standard way of using threads. So it's kind of semi-automatic. You don't need to do much. And you're going to use several threads, as many as possible. Yeah, thank you. Yeah, so what I wanted to explain here is that we use this library in order to use so-called wall time. So what is the wall time? Well, standard call to CPU time will return you so-called CPU time. What does it mean? Well, it means that if you use 2 cores, the time is going to be twice as large because it tells you how many clock ticks were used for executing this code, doesn't it? But this is usually not what you want to know. You want to know how much real time it took to execute, doesn't it? And this is not CPU time. So the real time, the way we all other clocks perceived time is it can be obtained by so-called get wall time or OMP get W time, wall time. And this actually counts real time. And you will see that when we execute this in parallel, the two times will not be the same. So if it's done in serial, then wall time and CPU time match, they're the same thing. But when it's done in parallel, then wall time is always shorter than CPU time because there were several threads. Okay, we use several cores. Okay, so yeah, so we start again here with implicit none because we want to define all the variables. And then here, the first statement here is actually defining that we have an external function. So it turns out that if we don't define here at the beginning of this program that there is a function that we just defined before, Mandelbrot, then this code will issue an error because, well, inside this program, it's not known what is Mandelbrot. When we call this thing, it's going to say, well, everything that we use inside this loop needs to be defined. Okay, and so therefore we need to define here at the beginning all the function names of the external functions that we're going to use. Alternatively, we could use modules or pack them into modules. Then we don't need to define them. But otherwise, we need to define here. Now, the good thing is that this Fortran is not too picky when it comes to definition. It's enough to just define what is the return value of this function. So you don't need to specify what are the input variables, although you can if you want to. Okay, so then we define here all the local variables that we need. So I and j are just counters. Then we have some real numbers, x and y, which will be a mesh in the x and y direction. Then we need a complex number z0, the same z0 that we need for the Mandelbrot set. Then here are certain fixed numbers, integer numbers. Nx is the number of points in x direction, ny is number of points in y direction. And then, of course, maximum steps is how many steps we're going to iterate this Mandelbrot set to determine whether it's part of the set or not. Now, this parameter here is equivalent to writing const in C. So if you're familiar with C or C++, there is something which is called const, which defines that this variable will not be changed. It's constant within this code. It's not going to be changed. It's not allowed to be changed. It's always useful to use this kind of parameter or const in C because this allows the compiler to optimize such variables more aggressively, and at the same time, it's going to reduce the errors of the code. Now, next, we define this real numbers. So this is actually a small array of 4 numbers, which specifies the limits of plotting. So the x goes from -2 to 1, -1 to 1. And now you see this is type of the way that fixed arrays, or well, actually, that's the way you can initialize an array in Fortran. So you have these brackets here, and then // That's the that's how, and all the values then have to be comma delimited. So again, bracket / bracket. That's initialization of an array. Now it's interesting that in C++, for example, this type of initialization was added very recently, just in 2011, I think. And it can be done with curly brackets. C++ didn't have that for a long time. Of course, Fortran has this square brackets for initialization, and this Python has square brackets for initialization, and this of course existed from the very beginning of Python. But interestingly, C++ didn't have that, while Fortran had this for a long time. So in some sense, there were certain things in Fortran that were kind of missing or abandoned in C++. Okay, so here there is an array. We specify a real array, Mande, which is going to have the dimension nx and y. And the reason that we define an array is we want to store the results in an array before we print them. Of course, we could immediately print the result on the screen and then, use gnuplot to plot, or we could use Python to plot. But the reason that we write it in an array is because we don't want to time the printing. It turns out that printing takes way more time, both in Fortran and in C and in Python, than calculating Mandelbrot set. Okay, so calculation is relatively fast. And to kind of avoid timing the printing, we are going to first save everything into an array, and then only later on, we're going to have another loop where we print, but we're going to time only calculation, okay, and speed up only the calculation. Also, OpenMP would be useless in printing because, I mean, different threads would then compete for the same output string, which, of course, doesn't make sense. Okay, so what do we do? This is now the main, well, this is actually the main loop. We first call timing. So both the CPU time, as we discussed before, is counted by CPU ticks, is being timed, and this wall time is being started. So both start and start W are basically floating point numbers, but I don't think they're the same. So what you need to do is, of course, you need to always call this clocks twice and then subtract. That will give you the timing. And I don't think they're allowed to be mixed because the starting time is different in the two, as far as I remember. And usually the starting time has to do with epoch time. Have you heard of epoch time? So it's a time in 1970 when somehow computer scientists decided to start timing the time. So it's number of seconds from year 1970 something. And so this routine, for example, returns you a floating point number of seconds after that epoch time. But you're not guaranteed that these two have exactly the same epoch time. I mean, might not have. So therefore, you always need to subtract two numbers.
Professor?
Yes.
I had a question. So when I was testing out the Fortran code,
yes,
first start W and finish W. When I did real, like for the declaration, it just gave me 0 when I tried to get the wall time. But when I did double precision, it actually works. So I was wondering, because in your code you use real and it worked, and I wasn't able to do that.
Yes, I mean, actually you're right. You changed this to real 8 and it worked?
I changed it to double precision.
Yes, which is real 8, yeah. Okay, thank you for pointing this out. Yeah, you're right. I mean, it's interesting that in my in previous version of in the previous computer or previous version of Fortran, actually, Fortran 10 or something, G10, that wasn't the problem. It always returned the correct number. But I noticed recently that it can return 0 sometimes, yeah, because it seems that the number becomes so large that when it subtracts, it can become 0. Yeah, it's a problem of precision of the number. So yeah, it seems that real 8 is now essential to use for timing. Yeah, thank you.
Okay.
Yeah, good point. Yeah, I noticed this year. Last year it worked. Okay, so what do we do in this loop? So this is the main loop. So we have two iterations. So our x component or y component from I is 1 to nx, j is 1 to ny. And so then here we specify the x and y variable on the screen. isn't it? Which goes between, well, the relevant limits, -2 to 1 and -1 to 1. So it starts with x1 and it ends in x2 when I is equal to nx. This variable y goes from x3 to maximum x4, isn't it? So it's kind of obvious. There's linear mesh, linearly uniformly distributed points. Z is then becomes the complex number, which contains x and y floating point numbers. And then this Z0 is the one that we need to give to the subroutine that we, or to the function that we just created, which needs Z0 and maximum number of steps, and returns back an integer, which is the number of iterations before we realize that this is either part of Mandelbrot set or not. And we're going to write this, in some sense, this was integer, but we're going to write now into real, as a real number. And the reason for this is because, well, when integers become very large, it's convenient to have real number. But even more importantly, we're going to print then 1 over this. And so kind of it's useful to have real numbers, maybe rather than integers. Although I think in this case, it will work even with integers, because integers are not too big. Okay, but what I really wanted to explain here, the reason that we are doing all this is because we are going to use OpenMP. Okay, so now by default, exclamation mark means comment. Okay, so it seems that these two lines here at the beginning and at the end don't do anything. Okay, because they're like comments. But if we compile the code with an instruction which is called -f open MP, so we're going to add this flag to the compiler, then all exclamation mark $OMP have special meaning. Okay, so this symbol here has special meaning. It means that this is OpenMP instruction, how to execute the code on multiple threads. Okay, so now we're gonna discuss this OpenMP directions a little bit more in the I think next time or soon. But this is probably the simplest OMP statement that you can make, which is parallelizing everything inside this double loop. Actually, we are parallelizing only the outside loop in this case. So if you write OMP parallel do, it means this is a directive that asks the compiler to parallelize this first loop as good as it can, as best as it can, or as good as it can. Okay, so since nx is large, this should be pretty straightforward to trivial to parallelize. So what's going to happen is that I is equal to 1 will go on one core, I is equal to 2 will go on another core, I is equal to 3 will go to the third core, and so on and so forth. And then once this first n numbers are used, then we're going to repeat the process and we're going to redistribute them on the cores in commensurate way. Okay, so this is how it's usually done. We can fine tune with this OMP statement how exactly we want this to be done. Do we want the first core to get number 1 and n and 2n and 3n, or do we want the first core to get number 1, 2, 3, 4 up to n-1, and the second core start with n and so on? Okay, so these are different possibilities. It turns out that we can specify how we want this to be executed with the more precise OMP directive, but currently we're not going to do that. We're going to rely on compiler to do its best. So, and we're going to just say OMP parallel do, and then the mandatory thing here to specify is what is private to the loop. Okay, so let me explain the concept of private versus shared. So when you do something in parallel, OMP parallel basically, there are two types of variables. There are variables which are common to all threads or to all cores. Okay, these are actually threads. So there are variables which are common and there are variables which are not supposed to be common because they're different. Each thread needs its own copy. Okay, these are the two possibilities. Now, what is typical common variable? Well, this array, 2D array, Mande, okay, is a variable which clearly it's common because different threads will just produce a part of the array. Okay, so one core will produce maybe one component, another core will produce 1-2 component or 2-1 component. And so therefore, all threads should share this array. Now, it turns out that by default, if you don't specify anything in this private statement, everything is shared. Okay, everything is shared by default. So therefore, we don't need to specify that Mande is shared variable because yes, every variable is by default appears like shared. So everything is being seen on all different threads on all cores. However, there are variables which clearly should not be shared. For example, variable j here is going to be different on each core. So I will on first core is going to be is going to go maybe from 0 to 1 to 2, but on the second core is going to go from 6 to 7 to 8. But the j variable is going to then appear different in different cores because they might not be exactly at the same time doing the same sub-problem. So this j, of course, needs to be different on different cores because it's an independent execution on different threads of that statement. Similarly, x and y will be different, and similarly, z0 will be different on different cores. Okay, so therefore, these variables, all these variables, need to be specified as private. Okay, we need to specify them that these variables here are different on different threads. Okay, and if you specify all the different variables on different threads, then you're done. I mean, nothing else needs to be done for the simple OMP statement. So the only exception here is that we didn't specify that I is private. Now it turns out that the first variable after the OMP parallel do statement, the counter for this do loop is by default private, so we don't need to specify it because it's kind of obvious. If we make a parallel loop, then the first loop counter has to be private, so it's always private. We don't need to specify it. All the rest have to go into this private statement. Okay, so what do we do? Well, we specify what is x and y. The point, we create complex number, and then we execute this Mande on the statement, and this is done in parallel. And then once we are finished, we call the timing. So OMP get W time, CPU time, and then we print out the elapsed time. Okay, so print out the elapsed time. Now this printing, of course, in each programming language, the printing is different and it's kind of awkward. So Fortran is not the most user-friendly when it comes to printing. Now, Fortran has a better print statement. So this one, for example, is also a print statement. And this one prints to the standard output, kind of modern way of printing. And it's not that different from Python print, actually. Reminds you a lot of Python print. At least Python 2.7 had print statements very similar to that. But in this case, we wanted to print immediately after we reach this point. Why is that? Well, because we don't want to. There are two types of printing in all programming languages. It's called buffered printing and non-buffered printing. So buffered printing means that the string is going to be printed on the screen only once enough data has been printed or being ready to being displayed. And that's done for efficiency reasons. So you don't want to constantly bother the computer to print out what has been thrown on the buffer, but you want to kind of keep the computer accumulating output strings And then only after there is enough strings available to output, we output basically a couple of lines at the same time. Okay, so this is the standard way all programs print on the standard output for efficiency reasons. However, when you have things like that, when you are interested in timing, you want to see this timing immediately. You don't want to wait until the code is finished. You want to display immediately when we come here, before we start doing the printing, because printing takes much more time than actually calculating. And so therefore we are going to write this thing with a different statement, namely we're going to print this into so-called standard error output, or basically standard log output. So all programming languages allow you to use so-called standard output, which is in C. It will be called C out, or standard output, and there is also standard error output and standard log output. Now, error and log output, at least on Unix systems, are one and the same thing. In C, you would call this, or in C++, you would call standard error output to be CERR, and standard log to be CLOG. In Python, I think these are called sys stderr or sys stdout. So every programming language has slightly different syntax of how to print on different outputs. But in this case, we want to print into the standard error output. And it turns out that in Fortran, you need to specify as a first variable something which is called unit number, and there are numbers. So 0 means standard error, 6 means standard output, okay, which is buffered. So if you see 6, for example, that means it's going to be printed on the screen with buffered output. If you see 0, it means it's going to be printed on the output with non-buffered. Okay, and then so this specifies the unit, and then the rest specifies how things are going to be printed. This is formatic string, so-called formatic string, and then we're going to, of course, print the timing, which is finish minus start, or finish w minus start w, kind of difference in times. Now, this formatic string, of course, is kind of troublesome because every programming language requires slightly different way of printing. Let me quickly explain what it is. So this, of course, clock time is kind of obvious. This is string. And then s wall time is another string, and then another string. So we have just a set of strings. But then in between the strings, we also have something which is called here f63 and here f63. Okay, so these two f's are clearly formatic strings for a floating point number, isn't it? So f means floating point, 6 means that we're going to take 6 spaces, and then three digits after comma. Okay, so that's what this f63 means. So it's not that different from what we use in C or what we use in Python. So in Python, the equivalent thing would look like this: $6.3f. Okay, so f would appear at the end rather than at the beginning, and we're going to have a $sign. Now, the reason that we need this special $sign in Python, and actually in Python this would be part of the string. So Python allows you to have formatic string as being part of the string, and therefore it requires certain special characters such as $. Fortran, as you see, this is not part of the string, it's actually separate from the string, and therefore it does not require a special sign such as $. So it's just f6.3 means it's not string, it's format of something. Okay, so that's how it works. Okay, anyway, so this is the output statement that will print the time, and then this loop is basically just going over all the data. It recomputes x and y because it turns out that it's faster to recompute X and Y than storing them and displaying them. In lots of modern numerical programs, if you have a simple floating point numbers, it's easier or cheaper to recompute them to actually store them. Storing takes time. So we recompute X and Y, and then we print in the output the X, Y, and here we're going to print 1 divided by this number of iterations, because that means that whatever is part of the Mandelbrot set will tend towards 0. Whatever is not part of the Mandelbrot set will tend towards it's going to be bigger than 0, closer to 1. Okay, so if it's 1, then means it's definitely far from Mandelbrot set. If it's closer to 0, then it's closer to Mandelbrot, being part of the Mandelbrot set. Okay, so this is the Fortran code. And so what we need to do next is we need to compile. So of course, Fortran and C are compile languages. So we need to compile it, and then we need to execute it. Now the compiling requires one to specify, well, I'm going to use gfortran, name of the code. And we want to use the so-called -o flag. -o means that the output code is going to be called mandf. Okay, this is going to be name of the executable. So if we don't write -o mandf, we're going to get some standard name for the output, which I think is a.out or something like that. So some yeah, not very useful name of the output file. And then this fopenmp specifies that we're going to use openmp parallelization, so multiple threads. And then -03 means we're going to use as much optimization as possible. So -03 is usually the fastest optimization. The optimization starts with -00, -01, -02, and -03 is the biggest possible optimization, usually. Of course, there is also a possibility of using -g flag, which means debugging. So basically, -g is going to be the slowest, even slower than -00, but it's going to produce lots of information which you can use when debugging the code. Yeah, so, and then we execute. So let me demonstrate this. We have a make file, so we could just type make, and make file will execute these things. Well, we'll compile everything that is in this directory. So make clean, for example, we clean it, and make will compile both. Now, of course, if I didn't have make file, then I would need to specify this, you know, in the command line to compile. Okay, so once we have the executable here, clearly we have it, mandf. Okay, so then we want to execute it, but we don't want to print things into the standard output, because it's going to just print a lot of stuff in the output, and it's going to take a long time before all the printing is done, and we're going to lose the data. So what we want to do is we want to so-called pipe the output into a file. So in the file name that we're going to give is mand.dat. So whatever is being printed on the screen by this code is going to go into mand.dat. But notice that things that are printed into the error output will not go into this mand.dat. The stuff that is printed to the error output is going to be still printed on the screen. Okay, so if you want to redirect both the standard output and standard error output, you need to write at the end something like 2 goes to the address of 1. Okay, so if you do this, then it means both the standard error and standard output will go to the same file. Okay, but we don't want that. We actually want to store data separately, but the timing in a separate place. Yeah, and we got that the clock time is 1.59, but the wall time is currently 0. Well, if we execute it once more, we get that wall time is 0.5, but clearly we have this issue that the colleague pointed out. it has to do with not enough precision of real number. So if you want to correct this, we change real to real 8, and then hopefully we recombile. And now indeed we see wall time that makes sense. So the precision was not good enough, and therefore it was jumping between 0 and half. Right now we do get decent numbers. So what you can see here is that the wall time is substantially smaller than the clock time, and this will give me, the ratio will give me how many cores were used. So in this case seems to be 6 times faster. So probably around 6 cores were used on average. 6 cores were used for my execution. Now, of course, how many cores are used, it can be tuned with something which is called OMP num threads. We're going to discuss this later, but so as far as I know, the default is that we use as many threads as available on your as many threads as the number of cores available on your computer. So I think I have 8 cores. So I think by default this variable is 8, but I can tune it if I want to. So I can say export OMP num threads is 1, and I'm going to now force that my code is going to execute actually with just 1 thread. Okay, and if I'm right, the wall time and clock time should match. Okay, so you see clock time and wall time are both 1.3. Okay, why? Because I specified that there's just 1 thread that I'm using, but I think 8 is what is default. So in this case, wall time and clock time are different. Unfortunately, no, actually wall time is still smaller. No, it's before it was better. So I guess we're going to use what, 16 10 threads. I don't have 16 cores though, but it seems that in this case, it's if you want to optimize wall time, then it's good to have 2 threads per core. It seems that this is the fastest. Anyway, so wall time now is reduced down to 0.2 compared to original 1. What was it? 1.3 maybe, yeah. So if non-parallel code needs 1.3 seconds and the parallel code needs 0.2, so this would be the speed up of 5. Okay, so with the 16 threads, I can get speed up of 5. So it's not as perfect. As you can see, the best possible speed up that I could expect if this was, let's say, in the theoretical scenario, the best possible scenario, it should be 8 because I have 8 cores. Okay, but clearly there is some issue here because I need to access here the same variable Monday with all different cores. They are not completely independent. So that takes some time. That definitely takes some time because I need to be careful when I write in the same variable the result. So that actually penalizes me so that the code doesn't speed up perfectly linearly with the number of cores. But nevertheless, it gives you a factor of 6, which is substantial. Okay, so now we have the data, but we don't know whether this has whether this is any good. So of course we could look at the data, mand.dot, but humans don't see much in this. I mean, there are mostly ones here at the beginning because you were at the edge. So we need to display this somehow. And of course we could display this with Python, but before we go into Python, I wanted to show you how to do this with gnuplot. So GNU can display simple density plot. So this is the code that you need for the GNU plot. So set view is map, and then you use splot, file name, and then this is with palette 3 and 5. So this is this tunes the colors, and then we need to do this pause at the end so that it doesn't kill the plot immediately. So then you can use gnuplot and the name of the file, and it's supposed to display. Now, displaying itself in gnuplot actually takes quite some time. I was surprised that actually GNU-plot is not that efficient on my computer. It used to be pretty fast in the past, but on Mac, it's not that fast. It takes quite some time to display. And Python matplotlib, as you will see later, is way faster. I mean, Python matplotlib, the same amount of data can display way faster. So clearly, Python has an edge compared to other tools on Linux. Okay, but anyway, Mandelbrot set looks correct. Huh? So that's what we wanted to check. So hopefully your code displays that correctly too. Yeah, so we finish at 1:30, I guess, huh? 1:30, yes. So we definitely have time for yeah, C++. But before I do that, let me comment very little on why do we still bother with learning Fortran. So we're not going to go much into detail with Fortran. I mean, this is more or less the almost everything that we're going to learn about Fortran in this class. Maybe a little bit when we go to F2Py, but we're not going to go deep into the syntax. Now, why do we bother with it? Well, because there is still a lot of scientific code written in Fortran, so we need to use it, and occasionally we need to adapt it to use in our higher level languages such as Python. It's very easy to integrate it with Python. So we're gonna discuss so-called tool F2Py and F2Py3. Actually, on my computer, the F2Py for Python 3 is just called F2Py now. But at the time when there were Python 2 and Python 3 available, Python F2Py3 was F2Py for Python 3, and F2Py was for Python 2. Anyway, so this is a tool which takes a Python code and creates a module which you can use just like any other Python module, and becomes a Python subroutine, Python code. Now, of course, for today's standard, this Fortran is obsolete. I mean, it's kind of old-fashioned. Of course, there's lots of this old-fashioned type of syntax. And this, primarily, the way I understand this is because, not only because it was developed so long time ago, 1950s, but because they wanted to keep Fortran back compatible and fast. So the primary goal of Fortran was don't sacrifice speed. It basically, I mean, Fortran is still the fastest language available because it doesn't have so-called aliasing problem. So you can't point with several pointers to the same address, because Fortran doesn't have a standard pointers such as C or C++. So Fortran will almost always beat C or C++. But unfortunately, because they always enforce so-called backed compatibility, I think that Fortran is kind of more clumsy to develop. Now, the issue, of course, is also that there are lots of versions of Fortran. So, I mean, I just named here a few. Fortran 77 was one that was very, very popular. Then Fortran 90 was another big upgrade that's extremely popular even nowadays. And but there's even Fortran 2008 and probably something after that. And those new releases actually add certain syntax to the language, but they always enforce back compatibility. So basically, I'm sure that all Fortran 77 codes will run when you compile them with the latest compiler, which of course, it's in some sense it's convenient because the old code is running, but it also means that language it has harder time to develop. If you compare this to Python, for example, Python 3, that is now the default Python, has been recently adopted as the default, and it made Python 2 obsolete. And Python 3 is not back compatible to Python 2, which is a major headache for all of us that have old code. So as you probably know, that a year ago or 2 years ago, 2020, I think, was when Python 3 became the only supported language, and Python 2 is now obsolete. So even the new computers will not come with Python 2 anymore. And so the entire, all the codes that were developed by Python 2 are basically obsolete now, and somebody needs to go through this code and upgrade. And it's a lot of human effort. So this, I'm very unhappy or very nervous about that decision by Python committee, whoever these people were, because the difference in Python 2 to Python 3 is relatively small. They could keep it back compatible, but they decided not to. But compare this to Fortran. I mean, Fortran 2008, or basically probably we have 2020 one version, it's back to compatible to Fortran 77, which is just many, many generations back. And of course, that makes things harder to modernize. Okay, anyway, so this was all about Fortran. Now, next step that we want to discuss is C++. And we're going to do the same. We're going to also do OpenMP parallelization with C++. And we're going to kind of compare the syntax, which one is easy or better or different. Okay, so the C code is in the manc.cc. And as you can see in C++, you have to include quite a lot of things, header files. So these are so-called header files. You have to include a lot of them just to do basic things. That's how it is. I mean, the developers decided that in C by default, or C++ by default, you're going to have very, very few things available. Partly this has to do with the fact that they want to avoid something which is called collision of symbols. So there are lots and lots of libraries, or include statement, possible includes and include files, and if you kind of allow too many by default, then the same variable can appear in multiple of them, and then the behavior depends on the sequence in which you include those files, and that's very, very troublesome. I mean, Python in some sense is very flexible, but I have some problems with this. Many times I noticed that some of the standard files, standard modules, such as SciPy and NumPy and matplotlib, for example, they have the same symbol and they collide. So how the code will execute, or how when the error will occur, can depend on the sequence of include statements. So, which is in some sense problematic. But at least in C, they try to be very careful and include very few by default, so that you as a user have full control of what you include. Now we need to include here IOStream, because this IOStream is standard printing, so printing to the standard output. Without that, we cannot print. We need complex numbers. Now it turns out that in C or C++, the complex numbers were not available until just a couple of years ago, maybe 10 years ago. Finally, of course, we have complex numbers that we need. Then the C time is the standard include for timing. Here, vector is include for the array, basically one-dimensional array, which is called vector in C. So one-dimensional array. Unfortunate problem in C++ is that there is still no standard multi-dimensional arrays available. I'm using a multi-dimensional array from Blitz++ library. So there's something which is called Blitz++ that was developed by Todd Wilsbacher, probably something like 20 years ago, something like that. But unfortunately, this has not been adopted as a standard. It has been used actually in developing Python NumPy. As far as I know, NumPy arrays are based on that implementation. But unfortunately, the developers of C++ decided that this is not default arrays, and default arrays don't exist. And that's, of course, a huge problem for numerics. I mean, if you don't have multidimensional arrays, it's really hard to work. And if you need to use something that's non-standard, the problem is that my code will work, but when I use this, when I share this with somebody else, there's going to be a problem. He will need to install this library. This library might not work with him because there is no maintenance behind these libraries, and that always creates lots of problems. So anyway, just make you aware why C++ is not the standard adopted type of code. Okay, so this statement here, using namespace std, means that we're going to use all the symbols that are in standard template library. So this is basically we say that namespace, current namespace that we have, which is the current environment, is going to adopt every symbol that appears in standard template library, which is called std. We're not going to go deeply into this standard template library, but let me mention that standard template library is the default library for C++. So this creates at least vector as a vector and complex numbers, for example. Without standard template library, we don't even have that. Yeah. Okay, so then we have this little function which does exactly the same thing that the Fortran implementation of Mandelbrot was doing. So it returns integer. So integer in C is int, not integer, but int. Then it comes the name of the function, and then it has to be followed by all the input variables. And here the difference is that in C, we specify the type of the variable just before the variable that appears. So Z0 is the name of the variable. This is the type of the variable. Again, the name of the variable, type of the variable. And then we don't need to specify here any types. So typically in C++ codes, we define type at the time when we need the variable rather than at the top of the program. So this kind of defining variables on the top of the program comes from old-fashioned codes, old-fashioned compilers such as Fortran compiler. So that's of course much more flexible then. So now what do we define here? So Z0 of course is complex number, which is complex of double. This means that it's not only this complex number, but it means that a real and imaginary component are going to be double precision numbers. Okay, so this thing here, lesser or greater, means that this complex is actually a template. It's a class in some sense. It's a class, but it's a template that can use here not just double numbers, but you could easily create complex of float or complex of integer if you wanted to. So this itself is another type, isn't it? So anyway, so here we have complex, which has also 6, but double is 8 bytes and complex is then 16 bytes. So the same as what you used in Fortran. And this const specifies that we are not going to change Z0 inside the variable. So this const is similar than in Fortran when we had intent in, but this symbol is even more important. This symbol here, this end here, means that we are going to use Z0. Z0 is going to be called by reference. So this is called a reference. Okay, so we're going to use Z0. It's going to be called by reference, which means that we are not going to create a copy of Z0 when we come to this, when we go into this program, but we're going to use Z0. The same Z0 that is going to be used outside in the main program, we're going to just use it inside. We're going to use exactly the same memory location for Z0 as the outside. So there are two ways to give variables to subroutine in C++. It's so-called call by reference and call by value. Call by value is the default one. So if you don't specify this, it's going to be called by value. The issue with calling by value is that we're always going to create a new local copy of this variable, and then we're going to work on the local copy of the variable. Now, this is many times what you want. The drawback of creating a local variable is that the code will take a little bit more time, because creating a local copy of complex number takes a little bit of time. So if it's in the inside loop, you want to optimize this out. So we're going to here use by reference, which means that it does not create a new variable. It uses the existing variable and just is going to just use but not modify. And then we also specify a number of steps, just like before. Now, unfortunately, we are running out of time, so I'm going to stop here. If you have any urgent question, you can ask. You can also stay after the class if you have a question. Any question?
So for max steps, why didn't you also use a reference for max steps?
Ah, good point. Thank you. Yeah, the reason for this is because if you use so-called what is it called? Simple types such as integer, double number, or a floating point number. In this case, the slow down because of using copy using call by value is minimal, or basically non-existent. It turns out that the compiler optimizes this out. So if you use standard types such as integer, floating point, or double, you can easily call by value. So not call by reference, but by value, and there's gonna be no time degradation. There is gonna be no price to pay for that, okay? Because they are simple types, and compiler knows how to optimize that, and it works really well. However, complex number is by default not one of those simple types. It's composed of two floating point numbers, and you pay a little bit of price. I mean, you don't pay a lot of price, but a little bit. Now, if you have here an array of numbers, then you pay an enormous price if you call by value. Okay, so the standard understanding is that, or the standard point is that if you have something that has lots of numbers, like an array, then you always need to use call by reference, because you don't want to copy a large array. Now, when it comes to just two numbers, you don't pay so much. It's just a little bit. But if you have just a simple integer, then you pay no price, and you can. It doesn't matter what you use, call by value or call by reference. Doesn't make any difference.
Okay, thank you.
Okay, so if there's no more question, yes.
Yeah, I had one question. So,
Yes, please.
when we transition in person, in the event that a student has to miss a class, maybe due to I'm an undergrad still, so due to college tours or something like that, would I be able to join online, or is there any way I just, I know you said you had recorded lectures from last year on YouTube. Are those, will those be kind of cover the same material as what we're covering in class?
Yes, they're covering the same material. The difference is that I'm not so sure if we're going to be able to do exactly the same timing. So okay. I don't know whether this is going to be exactly in lecture 2 or lecture 3, but close by, let's say. And all the material is also available online. So I think it should be pretty easy.
Okay, got it. Thank you.
You're welcome.
Also for the homeworks, how are the homeworks going to work? Because I saw that in the slides you have homework assigned. So do we just email those to you, or
yes,
how do you submit those?
Yes, exactly. So the idea is that you just email email me the results. Now for the homework 1, of course, to be honest, I'm not going to even check it very carefully because all you need to do is to install the code Where is the homework one? Yeah, install the code and make sure that the code works. Where's the homework? Here. Yeah. No, I don't know what's the first homework, but anyway, the first homework is just setting up the environment. And this is something that I don't need to check because you're going to see in other homeworks if the environment's not going to work, isn't it? So you can send me something like a plot of Mandelbrot that you succeeded, but this first homework is basically something that it's mandatory. You have to do it anyway. And then in the next homeworks, there is going to be well-defined output. I mean, you will send me some type of code. Okay, so I like to see your codes because the idea is that you kind of exercise in coding, in producing algorithms.
Okay, and then are they going to be due like every week, every 2 weeks? Like how, or is it just after
not
the
every
class?
week? I mean, once we finish certain chapter, I'm going to say, okay, so now you have a week to finish it.
Okay.
It's not going to be every week. No, I mean, we're not going to go that quickly. So certain things are going to be developed over three periods, which is 1 week and a half. Certain things maybe a little bit faster. So maybe every 2 weeks or something. We'll see
Okay.
how it works. Any other question? Okay, thank you. Yeah, I'm sorry to take you too much time. See you next time.